All right, welcome everyone to this session of Map Time Davis. I am glad to see all of you here today. My name is Michelle Tobias. I am the Geospatial Data Specialist at UC Davis Data Lab, and Data Lab supports a lot of our research and learning communities, including Map Time Davis, which is a product of the Spatial Sciences Research and Learning Cluster. Today's workshop is also a joint effort with the Davis Python users group. So we want to let you know that both of those things are going on in Data Lab. I'm going to post some links in the chat about that. So we've got the link to the Map Time Davis page, which has our schedule for upcoming workshops. And we've got some really cool stuff coming up later on in the next month or so. And also we've got a link to the Davis Python users group, which is another group that's getting started focusing on Python. They meet regularly to discuss Python things. So you're welcome to join that group and join our Python community on campus. I am also going to post a link to our YouTube channel for Map Time Davis. This is where the recording will be in a couple weeks. So if you need to go back and take a look at that, you'll be able to, or if you know someone who's missing today's session, you can share that link with them. Let's see. What else do you need to know? I think that's pretty much it on my end. I don't know, Nick, do you want to say something about the Python users group at all?
Just to add that we have regular meetings every other week. We've got a meeting coming up next week. If you're interested in Python, you're encouraged to join us. New people are always welcome at any level.
Yeah, I'm super excited we're getting that started because campus has needed a Python group for a really long time. So it's really cool that that's getting going. So I guess with that, I think we're ready to get our workshop started. So today, you all know you're here for our workshop on geospatial Python, which is again something that it's a topic we've needed on campus a lot. We don't have nearly enough Python workshops going on with geospatial stuff. I think it's really important. So today we have Ryan Avery from Development Seed, who is here to walk us through one of the new carpentries workshops on geospatial Python. So I'll let Ryan give himself a more thorough introduction, but thanks for being here, Ryan. I'm super excited for today's workshop.
Thank you, Michelle. Yeah, hey everybody. I'm Ryan, as Michelle said. Yeah, I've been working with geospatial Python for about 5 to 6 years now. And I'm really excited to show you this lesson today. A lot of the stuff that we're going to be teaching here are things that I wish that I had knowledge of back in my undergrad or my master's. And so the goal today is to make it easier for you to query, fetch, and analyze raster data. We might get to vector data, but maybe not because time is short. So I'm going to share my screen in a minute. Before I do, I just posted the link in the chat window to the lesson that we're going to be covering today. So I think it'd be good if everybody clicked that link and had that open as they go along the workshop. This is the lesson webpage, and it's going to show us a table of contents for the entire lesson. So I'm going to share my screen now. So yeah, if you click that link, you should be seeing something similar to what I'm seeing right now. This is a carpentries lesson. So what is the carpentries? The carpentries is an organization that seeks to teach folks, could be researchers, could be undergraduates, graduates, it could be professors, seeks to teach folks the fundamentals of programming. And that can be language fundamentals, like the fundamentals of Python, like what is Python, or domain-specific data science topics like geospatial Python or geospatial R. So I encourage you, if what I'm showing you today is new or covering like a lot of territory that you haven't seen before, to check out some of the other carpentries lessons. So in particular, at the top of this webpage, we reference the plotting and programming in Python lesson, which is a good like Python fundamentals lesson if you're not so familiar with Python. Yeah. And yeah, I think we won't spend too long on the intro, but just to sort of cover what we're going to be doing today. We're going to be working with satellite imagery from the Copernicus Sentinel-2 mission. We're going to be downloading this data all with Python code. And we're not actually going to be downloading any files. We're going to be fetching the data directly to our programming environment in our Jupyter notebook. We're going to be learning how to inspect the metadata for that, how to plot it quickly with Xarray, and just talk about some of the advantages of this style of workflow, of working with geospatial imagery. As an alternative to getting the data from a graphical browser like USGS Earth Explorer or something else, which might be a little more cumbersome to work with. Later in this episode, there are some vector data sets from the Dutch government. I don't know if we're actually going to get to those, but just to sort of cover what this lesson in full has in store. Episode 1 through 4 kind of cover the fundamentals of like geospatial and geographic data. So if you're unfamiliar with like the geospatial domain, like this would be a good place to start. If you're already familiar with this, you know what projections are, you know what coordinate reference systems are, you're familiar with tools like QGIS and et cetera, you know, raster versus vector, then definitely skip 1 through 4. So we're going to be assuming some knowledge of this as we go through the lesson and starting with episode 5. But again, if this is unfamiliar territory, definitely go back to these episodes. They're all free. They're all open. Anybody can go and run through these episodes on their own time. So we'll be doing episode 5, looking to get through episode 6. You can then also take a peek at some of the later episodes we're not really going to cover in detail, like how to work with vector data in Python, how to combine vector and raster data, and even getting into how to run computations in parallel with tools like Dask. So how to speed up your workflows when you're processing lots of imagery. Cool. And this lesson definitely doesn't cover everything, but it's a nice primer. Okay, so to start out, with these carpet shoes workshops, typically how they're structured is the learners who are participating are going to do as I do. So I'm going to be live coding. I'm not going to be like showing you a pre-made notebook. I'm going to be coding along, and then you can code along with me. If you don't want to do that, that's fine. You can just watch and enjoy. But you definitely learn more if you try to code along and do as I do. So to start out with, we're going to go to this setup page. Ideally, you ran through these setup instructions beforehand because they're a little lengthy, but I'll cover them briefly right now. You're going to open a terminal. So for me, my terminal is WSL. For others, it might be something else. In fact, actually, yeah, my terminal is Ubuntu. So I'm on a Windows machine, but I'm using Ubuntu. So for Windows users, I think the instructions have you install Git Bash if you ran through all the setup. For Mac or Linux, you can search terminal and open the terminal app. So to start, we're just going to follow all these instructions here. So I can change my directory to my desktop, or I don't have a desktop because I have like a little bit of a unique system here, but I'm going to start with the next instruction, which is making a geospatial Python folder. And I'm going to call that Geospatial Python Workshop. So we're going to go into that directory, and this is going to be where we're going to store all of our data files for the lesson and our Jupyter notebook that we're going to be working with. So when I start a new project, usually the first folder I make within that project folder is a data folder. So we'll make that data folder and see that it's there. And then we're going to download, in case you want to use these later, these vector data sets. And in case we actually get to this today, but I think that might be too ambitious.
Hey, Ryan, is
Yeah.
there a way you can make the font on your terminal window a
Ah,
little bit bigger? It's pretty small, I guess, for
Absolutely,
folks.
absolutely. Yeah, sorry, I forgot.
Oh, that's so much better, I think.
Okay. Yeah, I can even go one size. Yeah. So, okay. So yeah, I ran that curl command. So I'm just copy pasting the things in these setup instructions. I ran the curl command. And so now if we, oh, but I forgot to do that in the data folder. So let me just do that again. I'll go into the data folder and then I'll rerun that. So that way I have all the data files in the data folder. That should run pretty quick. And so now we see that we have these files in the data folder. No need to unzip these files because you can open these zip files directly from the Python vector libraries we're going to be working with. Cool. And so once you're done with that, the next step is lengthy, and I'm not going to go through all of these steps, but it requires having Anaconda on your system. So a way to test if you have this is to type conda and hit enter. And if you see output that looks like this, where it's telling you about the usage of the command conda, it means that you have the tool that we would use, that we're going to be using to install all of the Python libraries for the workshop. If you get an error when running conda, like conda not found, I would run through these instructions depending on your system. So there's a Windows tutorial, a Mac tutorial, and a Linux tutorial. And you can also type in the chat if you have questions for the helpers. And just, yeah, post your question and a helper will get to it. So I'm assuming you have conda. Once you have conda, you can copy this command to create the geospatial Python environment. So you copy, paste that, run it. It'll take a little bit. It might take a minute, it might take 2 minutes, but it'll complete. If you do have issues with that though, type in the chat. And there's some other instructions, you know, in case you want to try like a faster install method, etc. But I think we're going to get to the lesson now, assuming that you have gone through these setup instructions beforehand. So conda activate geospatial will activate your geospatial dependencies. So before this command, we don't have packages that are listed here accessible to us if we were to run Python. After activation, we do have these packages accessible to us. And so now that we have this accessible, we can run Jupyter Lab. You just need to type Jupyter Lab. I'm pretty sure you don't need to do this extra flag that I need to use. So just type Jupyter Lab and run that. I need to run that for my system. And then that should open your Jupyter Lab environment. And if you had trouble with that, yeah, just another reminder to check in to the chat. So what you should see is, you know, not any of these because we downloaded those to our data folder. So you shouldn't have anything in this directory except for a data folder with 3 files in it currently. And so now what we want to do is get started with the workshop. So you can click to go back briefly, like you can click this plus sign, you can go to click to create a notebook in this environment, IPyKernel, which represents your geospatial environment. A quick check to make sure all of that worked is you can try to import Rio X-ray. And if you see a 1 here, that means that that worked. If not, check in with the chat. Cool. So now that we have our programming environment set up, we're ready to go to the workshop. So very briefly, I'm gonna let's move. Cool. So we have the workshop link. And if folks don't know where that is, they can ask in the chat. I'm going to go to episode 5 accessing satellite imagery using Python. So the things we're going to cover here today are, where can I find open access satellite data? Like if I want to download Landsat and Sentinel using the tools we're going to talk about today, where do I even find that? What are the URLs? Where are the providers? We're going to talk about what is a Stack API and how can I use it to search for satellite imagery. And then finally, after I've searched for satellite imagery and I maybe have a list of images that I want to get, how do I actually fetch that down to my computer using Python? So let's jump in. So there's a lot of introduction text here. I think it's good reading, but we're not gonna read that verbatim. But the first thing that we're going to talk about is sort of exploring a Stack catalog. So Stack stands for Spatio-Temporal Asset Catalog. Satellite imagery is spatial and it's temporal. So Stack is very commonly used to as a way to store metadata about satellite imagery and organize all the spatial and temporal and other metadata in a way that is interpretable by tools that we're going to use today. So how do we discover how to get data sets with Stack? A good place to start is with this tool called Stack Browser. And the Zoom bar is blocking my access to that. Sweet, so I'll move that over here. Cool. So Stack Browser allows you to look at all the different Stack catalogs out there. Let's just pick a random one. Let's pick Radiant ML Hub. This is a place to publish machine learning data sets. And so they have all sorts of different collections that you can browse on their website, but this is the actual catalog that is interpretable by Python tools to download the data. So there's this example, land cover data set. Sometimes, there might be some kinks to work out, but yeah, this is an example Stack API that you can use. And so let's work with the Stack API that we're going to use today. We're going to use this element 84 Stack API. So you can just copy that link in the lesson page right here, and then you can paste that into this, and it'll Stack Browser will pop that up. So these are data sets that are hosted on AWS, so Amazon AWS. They're public data sets, so you can query them. You can download them. And the data set that we're going to be working with today is called Sentinel-2 L2A cogs. So these are surface reflectance cogs that I think they have the whole record starting in 2015 for the whole globe.
Hey,
Something
Ryan,
to note. Yeah. Sorry, Alex.
you want to tell people what a cog is?
Yeah, sorry, acronyms. So COG stands for Cloud Optimized GeoTIFF. So the key word there is GeoTIFF. So I think folks here, if they've opened satellite imagery in ArcGIS or QGIS, you're familiar with TIFFs or GeoTIFFs. A COG means that GeoTIFF is cloud optimized. So it means that it allows you to do some fancy things like maybe I only want to select a slice of imagery within this scene. Maybe I only care about a portion of this scene. So with a cog, you don't need to request the whole file. And maybe you can even request chunks of this file in parallel. So that's what we mean by cloud optimized GeoTIFF. Yeah, and plenty more to read about cogs and things in throughout this lesson, especially I think episode 4 of this lesson touches on it. Hopefully that's an okay description. Yeah, so some things to note about this stack catalog. This is all, Stack Browser is just rendering metadata that is associated with an entire catalog or with like an individual scene like this one. And all of this is like interpretable by Python. For this particular item, for this particular scene, we can get a look at like all the different assets you can download. You have the capability to show this on a map and get a preview of it before you even download it. You can click a download button to download like some of these assets. And yeah, this is pretty powerful. The reason that this is powerful is because Stack is a metadata standard that not just Sentinel can use. Landsat, there's also a Stack catalog for Landsat. So you have a very similar standard. You have a standard that works for both Sentinel and Landsat. So you don't need to learn a new way to download Landsat data or a new way to download Sentinel data, which is common if folks are using GUIs like USGS Earth Explorer or Copernicus Open Data Hub. You have to like learn a new way to download each new data set. And so with Stack, that makes that process easier. So enough talking, let's get to some coding and actually pull down some example data. So we were just looking at AWS Earth Search, those AWS open data sets. And so we're going to create a variable that has a string that is just the URL to that Stack API endpoint. And .element 84.com/v0. The first library that we're going to use is called PyStack client, and we're only going to import one thing from that. We're going to import a client class, and then we're going to open the API URL using client.open. So what did we just do here? This is sort of like us, like we are the client. We are opening this like URL. It's sort of like opening Earth Explorer or opening like your browser and going to the place where all the data is. So we have our client. It's aware that we're going to be working with the Earth Search Stack API. So let's specify what satellite data set that we're going to be working with. So let's make a variable. We're going to work with what we were just looking at, the Sentinel L2A COGS, Cloud Optimized GeoTIFFs. And L2A is cool because it's surface reflectance. So not just top of atmosphere, but it's got that atmospheric effect removed, so it's surface reflectance. So we're going to be using the same ID for this collection that we're seeing here, Sentinel right here in the URL, Sentinel S2 L2A COGS. We're going to use that same ID here. So Sentinel S2 L2A COGS. Awesome. So next, usually when you're searching for imagery, you care about a particular area of interest. So PyStack knows how to interpret a variety of different ways to specify that area of interest. You can specify it like a point, a bounding box, GeoJSON, or a Shapely object. Shapely is a library for working with shapes in Python. So we're going to work with a point to specify our area of interest. So we're going to import point, then we're going to make a point. And yeah, so we're not downloading imagery yet, but we're going to search the Earth Search catalog for imagery that intersects our collection ID. So we don't want like Landsat, we want Sentinel. So we're going to say collections equals collections takes a list of collections, but in this case, we only want to filter on one collection. We're going to say it should intersect a point. And we'll say, I think this would return hundreds of items, hundreds of Sentinel scenes. We don't want to work with hundreds of Sentinel scenes for this example. So let's say only return 10 max items. And I think this point might be representing somewhere over Central Park, but I forget. Cool. And then we can type search.matched to see like how many results were returned if we ignored that max items argument. And then we can then actually get the results of our search, including the max items argument. So the result you should have is a PyStack item collection. And what is that? So we can look at the length of this. You can see that there are 10 items here, and we can iterate over this. Items, and we can see what this tells us. So each of these items represents an individual Sentinel scene. We haven't downloaded it yet. We just have the metadata for this right now. But we'll see that it's very quick to download and fetch this in a bit. Cool. So I'm going to pause a little bit here and just briefly mention one thing that might come up. With any service that's providing imagery, there may be hiccups. Something that I discovered just today is when I tried to open this API URL, sometimes I would get like an internal server error. But then when I would rerun this cell, it would work. So I guess the lesson here is like some of these Stack API URLs, they're more stable than others. I think in particular, when we created this lesson, this is like kind of one of the first run throughs of it. This is the version 0 of this Stack API. And now there's a version 1 that maybe we should be switching to. So just if you ran into that on your end, understand that that is the reason. And hopefully that's not going to inhibit too much from you being able to follow along. Yeah, definitely speak up in the chat if you run into issues like that. Okay, so after that interlude, we have these items which represent individual Sentinel scenes and the individual Sentinel scene metadata. So let's now work with like one of these items individually and see what we can learn about it. So we're gonna index this item collection like it's a list and just pull out one item. We're going to look at the date time, see when was this scene acquired. So it looks like it was acquired 2022 in October. Cool. And we're going to look at the item geometry. What is the spatial footprint of this scene? So we get this rectangular box representing the scene. I think that this, this is not like, how do I say this? Not like along the orbital path. This is like the rectangular bounding box around the scene, including like no data values in the corners where like the imager didn't acquire data. And then we can look at item properties. And we can get all of the metadata we just looked at and some more. So we can look at the instrument, the ground sampling distance, which is the resolution. We can look at the cloud cover, pretty important variable, and yeah, other aspects as well. So now let's just show how you can make a new search by filtering on cloud cover. And then let's also add one other change, which instead of filtering on a point, maybe it's a little more common to filter on a bounding box. So let's do that. So to create a bounding box, first I'm going to take the point that we have from Shapely. You can call .buffer on that, and then get the bounds on the buffered point. And so now we have a tuple representing our bounding box. And then we can make a new search variable. And we can pass in our collection again. Hopefully my slow typing is an asset to be able to follow along. And then we can also, let's also throw in that we want to specify a date time filter. So we can, this is how you do that. So the slash indicates everything starting at this date and ending with this next date. Okay, so we'll do that for a 10-day search. And then finally, there are all these different properties that we could potentially query on. So we'll specify a query argument and take this EO cloud cover property that's here. Take that EO cloud cover property and say every scene that has cloud cover less than 10%. And then let's see how many matched results we get from that. Cool. So there's 4 scenes that are not too cloudy within this 10-day range that intersect this bounding box. So something that's good to do for reproducibility, maybe folks have heard about this concept that like reproducibility is really important. So folks can like check your research results and makes collaboration a lot easier. A good thing for reproducibility is if you are like getting all of your satellite imagery with a stack query, this query can change over time because new imagery is ingested into some stack APIs on like a consistent basis. So when Sentinel-2 collects more imagery, that is automatically ingested. So that can change your search results potentially, depending on how you're specifying your date time or your bounding box search. So it's a good idea to save out the results of a search. So we can save out this search by first getting all the items. And then saving that item collection using its save object method. And we'll save that to this JSON file. Cool. And so now if someone else loaded up this JSON with PyStack, they could, and we can just take a look at it. It's a feature collection, and it contains all the info they would need to get that item collection in their own notebook. Cool. So moving along, let's now, we've looked a lot at the metadata. So how do we actually access links that point to the TIFF imagery, the cloud optimized geotiffs? So those are called assets. Some assets are geotiffs, some assets are other files. But here, the assets that we're working with today are going to be geotiffs. So the assets basically represent the data. So we're going to see each item has an asset or a list of assets. It could be a list of assets, it could be a single asset. And we can look at those right here. So each of these Sentinel scenes has a thumbnail, which is like a small JPEG image. I'm not sure what an overview is, to be honest. I think it's a low resolution version of the image. There's some info, some metadata assets. There's a 3-band visual asset. And then these are like these surface reflectance bands that you might want if you're a scientific user. So all the Sentinel-2 bands are here for this scene. And yeah, those are the assets. So let's get a little more information about these because just these identifiers may not be enough. So if we do assets.items, we can iterate over this. So this is a dictionary now that has a lot more information, including links to each asset. So we're going to say for key and asset in assets.items. We're going to print out a string that's organized so that we print the key first and say that this key goes with this asset name, this asset title. So yeah, the overview is a true color image. There's an info asset that has the original JSON metadata from Copernicus, the original Sentinel-2 provider. And then that metadata is also provided in XML format. And then, yeah, some more details on these bands, I guess, is here. Not for every band, but you can see that band 1 is this coastal. We have RGB here. NIR is really commonly used for NDVI and other things. And then the SWIR bands are useful for indices related to moisture and a bunch of other things. So cool, we got like, kind of have a sense now of like what is present with this Sentinel-2 scene and what we could conceivably fetch programmatically. So we also saw when we looked at assets.items that we're close to being able to get the actual links to these assets and work with these. So a good way to do that is we can index this assets dictionary, and we can get, let's take the thumbnail and see what that looks like. It's this asset object, and we can get the href. I think when I look at href, I think of URL. It's the URL to that thumbnail asset. And we can just click on this and get a look at it. So this is the same sort of thing we were looking at in Stack Browser. So this is that Sentinel-2 scene. This is over Amsterdam, I believe. And that's pretty cool. But now let's look at how we can, if folks have worked with NumPy, maybe you've, oh, I see Alex's hand.
I was just saying
Alex?
this seems like a good stopping point to let everybody catch up for a few seconds here and see if some more questions come through.
Okay.
It looks like
sure.
we're having a few people who are having issues with the API returning some strange results.
Okay, alrighty. Yeah, sounds good. So is there a question that I should address for the group?
I don't think so. Have you had any issues with the API giving you errors related to transactions not supported or href references? Or have you, I remember earlier today you were telling me you had some other API issues.
So, yeah, so the API issues that I ran into, which by the way, I solved by just like rerunning the cell. And by rerunning the cell, I mean like rerunning, like opening the API and then like rerunning everything. So the thing the things that I encountered were like internal server errors when I would run like client.open. So by rerunning that, I got around that. I didn't see anything related to transactions but maybe I missed that.
It's entirely possible it only happened to a few people. So what I would remind people, which I've said this in the chat also, is that all of this code that you're seeing is in the lesson on the website. So you can always go back to the lesson and copy and paste. If you think you typed something wrong, or you're not sure if you typed something wrong, you can go back and look at that to see if that helps fix your code.
Yeah, and I'll just paste that. Oh, it looks like somebody already pasted the episode link. Thank you, Nick. Yeah, sorry if folks are running into those issues too. I mean, yeah, I did not see these issues when I demoed the lesson last week. So apologies. So are there other questions I should address, or should I pick it back up with looking at some how to load the data into X-ray?
I think you're good to go ahead.
Okay. Cool. So like, it's really useful to be able to look at the links, but how do we actually start working with this imagery in Python? So we already imported Rio X-ray, but just to make sure you all have it, I'm going to do this again. And we're going to open the coastal band of this scene. Maybe we're really interested in the Amsterdam coast. So let's open band 1 and make a variable for the link to that asset. And then let's open that link. So this is already, I think, something that, you know, it blew my mind when I first saw it. Hopefully it's blowing someone's mind out there, is that you can open this hyperlink directly with this function open Rasterio. And let me just so that gets across, so you see like what we're opening. You know, instead of downloading the file, making sure it's in the right folder, and all that jazz, we're just passing in this URL, which isn't changing, stays the same. We're passing in this URL to this open function, open Rasterio function. And boom, we have the data. Pretty cool, in my opinion. So this is now like, we're ready to run calculations on this coastal band. So you could think of like a scenario where we would make a for loop that would go through all of the scenes that we're interested in for a given query, opens them, and then puts them in a data structure that looks like this, X-array. And I haven't really talked about this yet, so let's talk about why this is cool. What is X-array? So folks probably have seen NumPy arrays, which are you know, they're useful. They're good data structures for satellite imagery. And there's all sorts of things built into NumPy and like the SciPy ecosystem to work with array data. Whether you want to do time series analysis, or stack the arrays together, or subset them, if you want to calculate statistics on them, if you want to do something fancier like run a machine learning model and predict segments in satellite imagery, you know, NumPy arrays are great for that. But it can be tough to like interpret like what's going on with this NumPy array, like what does it represent? Because we don't know what these dimensions are. The dimensions, you know, we can only really look at the shape, and maybe that doesn't tell us all we want. So instead of having your array look like this, maybe you'd rather have it look like this, where you're getting all this other information that X-array provides, like the band dimension. You know, we can see how many bands are in the image, and we know that that one represents the band. And then the Y and the X, you can you can actually look at the actual coordinate values of those. So already this is telling us something that maybe, that maybe the data is not in a geographic projection. It's not in latitude, longitude. And yeah, there's a bunch of other advantages to X-ray. It plays well with DASC if you want to parallelize computations, etc. And it also contains a lot of the same metadata that we were working with when we were working with PyStack, the results from the PyStack search. So X-ray preserves a lot of that metadata. Cool. So, but let's say you wanted to load this into QGIS. Like, let's say, okay, cool, I got it with Python, but I want to use it with a different tool. So we can quickly save that out to a raster, to a GeoTIFF. So yeah, this X-array, because we imported Rio X-array, we get access to this .rio thing, which is called an accessor. This gives us access to raster and like geospatial specific functions that you wouldn't have if you just imported X-array. So it's sort of like, you can kind of think of like Rio X-array as like building on top of X-array and giving you like geospatial like specific functionality. So we're going to save this, and then boom, we have this TIFF here. Okie dokie. Yeah, I think we should run through an exercise now. And I'm going to give folks a break from me talking for a little bit. So we're going to do this exercise for, let's say, about like 4 minutes. We'll come back, 256, 257. And I'd like folks to go back to this episode. So the exercise, downloading Landsat 8 datasets. So let's now kind of use the skills that we've been seeing, like opening Stack APIs with PyStack, creating a search, getting the items from that search, and then inspecting the items and then getting the links to the assets from those items, and then opening the assets. Let's use those skills with a new data set, Landsat 8, and a new Stack API, so NASA's CMR Stack API. So this description of this exercise has, I think, all the variables that you need to work with, to fetch some Landsat 8 data. So the goal is to take this Stack API, search this collection, HLS. HLS is actually harmonized Sentinel and Landsat data. So it's a nice collection because if you wanted to get Sentinel and Landsat data that is aligned, like this is a good way to do that. So HLS is the collection. Grab that data from some dates between February to March 2021, maybe a 10-day period, and then search over this point coordinate. So using the intersects. So you might need to use Shapely. And then finally, the asset that I want you to get is this browse asset. So let's actually, so now that I've done that description, let's actually come back at like 2:58, give folks like 4 minutes to tackle that, or take a breather, stand up, stretch, and then I'll come back and we'll run through the example. Helpers are doing a great job. I'm just now looking at the chat window. Thank you. Thank you. So I see a question. I'm apologize if I'm mispronouncing, but Mahesh. So you're trying the conda create command, and you say that this does not allow you to install.
Yeah. It says no command.
Yeah.
So
Yeah, it says command not found probably. Does it say
Yeah.
conda command not found?
Yeah.
Yeah, so that means that you need to, I'll point you to where you need to go. So
Yeah.
what you need to do is you need to go to the setup instructions. So I'll paste the link here.
Yeah, that's true. But the thing is that I am using my office laptop, so that it doesn't allow you to do it.
I see.
That's why I am trying to do. If I can use existing Anaconda,
I see. Okay.
And that's why I got the problem.
So one other suggestion then is, so I think you understand that like one solution is if you had control over the laptop to install Anaconda. But since it sounds like you can't do that on your office laptop,
that's it.
on your office laptop, you can try to search for Anaconda prompt. And Anaconda prompt could be an alternative that does have access to Conda. And so I would try that. If that doesn't work, I would maybe post in the chat again. Helpers can help out.
Sure.
Yeah. So we have about one. Yeah, no problem. We have about 1 more minute for folks to check out this exercise. Good question from Emma. No, you do not need to set up the environment every time with Conda Create. So Conda Create will actually, a cool thing to do is like, you can, I'm going to make a new terminal window. We can like look at where does this environment actually live. So we have the geospatial environment activated. And as you just saw, I just opened a new terminal and I ran activate again and it was still there. So you do need to run activate every time if you wanted to have access to the dependencies, but you don't need to run create every time. So this would be what you would run. And then we can look at which Python to see where this environment lives. So you can see that we have this mini conda folder. We have an environments folder, a geospatial folder, and we're using Python in that geospatial environments folder. Yeah, Naomi, I think I would just see a link as well if I printed the href. So I think that is working as intended. Hopefully that answers your question, Emma. Okay, so we're gonna move forward with this exercise. So we're gonna switch over to the notebook. Okay, so let's first scope out, okay, what do we do? Like when we want to work with a fresh Stack API, first thing to do is like define the API URL. So here we're working with NASA CMR, Earth data, yes, and okay. And we also want to then pass that to our client. So client.open CMR API URL. We want to set up the search. So, oops, search equals client search, and we want the collections to be what's listed in the exercise. So HLS L 30 v2.0 and intersects. We'll just quickly make a new point. -73.97 40.78, and then date time equals using that string format that we saw before. So where the slash tells us between these dates. Okay, and now once we have that search object, we want to get all the items. So all the items contain all the metadata, including the asset links. So we have our items, and then we can see how many we got. We have 5. And then let's sort the items by cloud cover. This wasn't in the exercise, but can be maybe a common workflow. So sorted items key equals lambda. We're going to make this quick lambda function and iterate over this items list, and it'll sort based on this property. So cloud cover. And let's get the 0th item, which will be the one with the least cloud cover. Oops, I typo. And we have this individual item from Harmonized Landsat Sentinel. And let's print out that that browse asset link. And then go to that. And boom, that's pretty. So congrats if you took a stab at that, if you got through that, way to go. You're well on your way to writing Python code to navigate stat catalogs. And let's just like sort of recap a couple things. First thing I want to recap is with this exercise, again, not all stack APIs are created equal, and I would say like folks are still learning how to like adopt this way of doing things, this way of filtering metadata and programmatically accessing imagery. A case of that like kind of learning as we go is the NASA CMR stack doesn't support the same cloud filtering that you see up here with the Earth data stack. So I just want to point that out. It's less than ideal, but this sort of stuff is getting fixed, especially if folks raise GitHub issues. So that's one thing. In case you were going to try to go use NASA CMR to filter by cloud cover, this is why we show, how to do a search without cloud cover filtering and then do the filtering on your own end, like this. The next thing is that even though a stack API may have public data and it's like free to download, there might be it might be protected, so you might need to provide authentication. So this particular asset that we're working with is this browse asset. It's pretty low resolution, not a lot of data compared to the actual like surface reflectance bands. So the surface reflectance bands, you can't just like download and like pull these off NASA CMR without having a NASA CMR account. So there are some steps listed here if you were to actually use NASA CMR to like get that data. So yeah, you need to create an Earth data login. You need to set up a file on your computer with credentials. There's instructions. And then you'd also need to define some environment variables, and you can do this in Python or Bash. Yeah, just some caveats with Stack and some gotchas there. So definitely go back to this lesson if you run into those and read, and it might help. So some key points that we just covered are that accessing satellite images with the Stack API, the provider's API, it's more reliable and scalable data retrieval. So if I wanted to, say, get every Sentinel image that intersects Amsterdam since 2015, it's going to be more repeatable to do that with Stack, what we've showed today, than going to a graphical interface and having to do that each time. So it makes it easier to reproduce the results. It's more scalable in that you don't need to spend a lot of time doing it necessarily once the script is written. There's other advantages. So Stack catalogs can be browsed and searched using Stack Browser if you want a graphical interface, but also by Python scripts. And then Rio X-Array works well with COGS, cloud optimized GeoTIFFs. So it can open GeoTIFFs from a URL link, and then you have access to it in an X-Array data array, and you can start doing calculations with it. So it removes a lot of steps like downloading and figuring out file paths. Cool. So we're gonna shoot to end at like 3:50-ish, but we're gonna keep on moving to episode 6, which is now that we have some data that's been read in, let's actually start plotting it and visualizing single and multi-band raster data. After we get a quick look at that, let's start looking at like the projections in more detail, because this is often something that we need to work through when combining multiple data sets together, multiple imagery or multiple vector data sets. And yeah, we'll look at it maybe a few more things about like the Rio X-Ray and X-Ray packages, like calculating statistics, etc. And then handling missing data. What if there's missing data? How does that affect our visualizations? How does that affect our plots? How can we account for that when we're doing calculations? So these are all things that we'll look to cover in the next 40-ish minutes. Okay, so we're going to start off assuming that maybe we're a collaborator of myself in episode 5, and now I've been given this search.json, and I need to work with this search.json. So that's why we saved that out before. So I'm going to open that up. So import PyStack as if we're starting a fresh notebook, and then we're going to open the item collection from the file. Okay, and yeah, we'll also, as if this is a new notebook, import Rio X-Array, and we're going to open band 9 of the first item here. So let's call this raster Amsterdam band 9. And what is band 9 again? Let's look at the Stack browser to figure that out. I guess band 9 is somewhere between NIR and SWIR, maybe, if they're ordered by wavelength. Maybe someone can type in the chat if they know. I don't remember. So we're going to open this. So open Rasterio again, and we're going to open a link. We're going to do this all in one line just because we can. We're going to get the 0th item. We're going to get the assets for that. We're going to index that assets dictionary, get the 9th band, then make sure that we get the link. So when we run that, boom, that didn't take long at all. And now we have this 1-band X-ray data array. So yeah, there's some geospatial metadata here that we can start inspecting. But just right off the bat, because we haven't really done the cool thing yet, which is plotting, let's plot that. So by calling .plot, we instantly get a pretty nice looking plot of this band. We have some clouds that we can clearly see, some water features. Looks like there's clearly urban area here, and like this no data piece that we'll look at working with later. So cool. We can plot this really easily. We'll look on improving this plot later. But let's now kind of switch back to thinking about, okay, let's understand the metadata about this. Like some questions come up in this plot, like what units are the X and Y spatial coordinates in? That's a question. Another question is like, what is the no data value here? Because we see that there's some valid spots that look like water, and then there's like some not valid spots that look like just, the Sentinel-2 didn't acquire any information here. So what is the number used to represent this and this? We want to see if they're different or the same. It can be really important for calculations. So let's start off by looking at the projection. So band 9, recall that we need to use .rio when we're working with X-arrays that have been opened with Rio X-array. Got to use that .rio when we want to do geospatial type stuff, like looking at the coordinate reference system. So we see that this is an EPSG 32631. Okay, we'll revisit that in a bit and see how to get more info on that. But we can look at the no data value. Cool, okay, the no data value is 0 here. So that's important to know. Maybe less than ideal, because maybe sometimes you want a no data value that's different from values that maybe are at 0 here or close to 0 over water areas. We can look at the bounds of this. So .rio.bounds, and we get that tuple format that we saw before when we were doing PyStack searches. And if we wanted to see like the width or the height, we can get that in a bunch of different ways. But one way we can get it is by, doing something like this. Cool. And yeah, something I briefly showed before but didn't really talk about, it was more to illustrate a point. But what if we want to get this as a NumPy array? Like we don't want all the metadata that comes with the X-array. We can call .values. And that is something that is available for all X-array data arrays, not just those that are opened by Rio X-array. So .values is going to show you the NumPy array. Cool. So let's take a break from metadata, go back to this plot. So knowing that the no data value is 0, we know that like a large fraction of this image is 0, which is maybe screwing up our ability to look at some of the variation over areas that do have data. So we can improve how we like the values that we're stretching our color histogram on. So here we're stretching this color histogram from 0 to 14,000. So instead we can, a really good like handy argument that I find myself using a lot is this argument to plot, where we say robust equals true. And what that is going to do is it's going to stretch the color histogram now between a shorter range. So from 0 to 7,000. So here the clouds maybe were affecting things a bit, and now they really pop and we can see more variation here. It still doesn't really address like that, you know, these are the same color roughly, and maybe like hinders interpretation of like where the water starts and the no data starts. So if we wanted to be more specific about that, we can instead set the visualization minimum and maximum directly. So we can say Vmin is 100, Vmax is, let's say 7,000. Oh, and I guess what this will do is like it'll affect the visualization of variation over land and like in water areas that are close to 0. But this is still going to look like the water body areas. So we can look at how do we address like and actually mask out this no data here. So when we open our data set with Rio X-ray, I'm just going to copy that and paste that down here. A good argument to supply is masked equals true. And what this is going to do is it's going to replace no data values, whatever that no data value is. It could be 0, it could be -99999. It's going to replace that with NaN values. So if we look at this file now, we see NaNs. So this is like a NumPy specific no data value type. And so now when we plot and we say robust equals true, our plot is starting to look a little more interpretable, where we clearly see that this is where data was acquired. Okay. So let's quickly hop back to looking at projections, because I think that we've like looked at the EPSG code, and just as a reminder, this is .crs. You know, we have this EPSG code, but maybe we're not very familiar with EPSG codes, and we want to actually understand more about the projection. So to do that, we can import this library called PyProj. Oh, and actually, instead of importing it, I'm going to say from PyProj, let's import the coordinate reference system. So the EPSG code will assign this to a variable. So .rio.to EPSG. What did I do wrong here? Oh, I forgot. It's the CRS object here that has the two EPSG methods. So that was a typo. So yeah, without the typo, that works. And then we just need to pass in this EPSG, which is an integer. Oops. So this integer to the PyProj CRS class. So we'll pass that in. And then if we print this out, now we get a ton of information about this projection, which is pretty cool. We get some information like the name. So this is a UTM, popular projection in meter coordinates. So we see the meter coordinate information here. We also get some helpful description, even like a pretty detailed description of the area of use, like where should you be using this projection? Where is it valid? Yeah, the bounds of the area of use are there, and yeah, the ellipsoid that's used for the projection. So good detail. And if you even wanted to like programmatically work with this output, so using the CRS object we printed out here, we can even like individually look at the area of use if for some reason you needed to parse this information. Cool. So let's get to looking at some raster statistics just to kind of show what X-ray and Rio X-ray can do. So I want the minimum. Dot min will return the minimum. If you want the maximum, you might be able to guess it's dot max. And these values you can access as, you know, not data arrays by doing dot values, just like any other X-ray data array. What if I want the standard deviation? Can do that, and there's the standard deviation. And this would be affected by whether or not we used the no data value or masked the no data value. So masking and replacing the no data value with NaN values can be a really important step that can affect your calculations. Yeah, and I think that let's jump ahead to working with 3-band imagery, because some of these things are going to change, like plotting and the methods that we use for that. So let's make a new variable for a 3-band image. We're going to still use open rasterio, and we're going to still go to the items. We're going to get the 0th item, the dictionary of assets. We're going to index that dictionary and get the overview. And then we're going to make sure that we're supplying the URL from that asset. So with href. And so now let's look and see what this looks like with the X-ray output and how it might look different. So this is a 3-band array because this overview has RGB, so RGB bands. It's much smaller than the band 9 we were working with. If we scroll up, I think this was, you know, almost 2000 by 2000, and this overview is, you know, around 340 by 340, and we still have all this metadata associated with this X-ray. So let's try something that's not going to work exactly as we expect. Let's try to plot it, similar to what we did before. So when we plot this, we don't get an image. We get this histogram. The reason for that is because dot plot is going to work differently depending on if you have a raster that is shaped, a raster that is shaped with 1 band. So here we have 1 band versus a 3-band raster. So for the 3-band raster, it flattens all the dimensions into 1 dimension and then plots the values in that image as a histogram. So to get around that, just something to remember for 3-band data specifically is .imshow. So .plot.imshow is what you use for 3-band data. And then boom. Yeah, with this, we're not maybe seeing something that looks a little stretched, which maybe isn't ideal. So just know that you can supply arguments and look at the documentation for these plotting functions on the X-ray documentation, or matplotlib documentation can be a good reference because under the hood, X-ray is just using matplotlib. and you can maybe change the size of this plot and improve it. Okay. So some key points here, and then maybe we can break for sort of, I think there might be some questions out there. So some key points. Rio X-ray and X-ray are for working with multidimensional array data with a similar grammar to Pandas. So Pandas allows you to, subset Pandas data frames with a syntax that is similar to X-ray and Rio X-ray. You can also call like .min and .max on Pandas data frames. You can also do that with X-ray. So yeah, that's another advantage of X-rays. If you're familiar with Pandas, X-ray and Rio X-ray might feel familiar and be a good Python package to work with your satellite imagery. Rio X-ray stores the coordinate reference system information. And it's stored in that like .rio accessor. So the CRS object that's accessible from .rio, you can get the EPSG code. You can use PyProj to, get a lot of detail about the projection information if you need that much detail. A lot of times the EPSG code will work if you're trying to reproject data sets, vector data sets, or raster data sets. Missing data in rasters are important to account for. So understanding the node data value for your data set can be really helpful, help you diagnose bugs that come up in calculations or in plotting. So it's a good idea to, as you're working with the data set you're unfamiliar with, look at the node data value, think about how that could be affecting your plots and your statistics. Okay, I think we'll break here for questions, and yeah, depending on how long that takes, that might be how we wrap up the session. Are there any burning questions out there that the helpers are aware of, or?
Yeah, I think one thing that was a little confusing with the overview is that it looks like it came in unprojected to most people.
Mm.
It seems like it came in projected for you for some reason.
Okay.
And so I think one thing that might be important is how people might make a 3-band image from the full resolution source data.
Cool. Yeah, good question. So we can touch on that a little bit. First, okay, so the first thing I'll do is like, let's take this example. Like we have like band 9, or let's take like band 4. And then let's take the other RGB bands. And then make variables and like show how to combine these. So I can import, and this is me kind of like working off the fly. So sometimes I very often have to look this stuff up, but I think X-ray has a method called stack. Oh, no, it doesn't. VStack? You know what I'm trying to do, Alex? I'm trying to look at like a X-ray stack. Okay, so data array.stack. So if you have an X-ray data array, I think you can stack multiple bands together, but this might not actually be the correct method to do so. X-ray.merge is looking more correct.
Yeah, I think you want to do merge, Ryan.
Cool. Yeah, so xr.merge. Yeah, xr.merge. And then we can make a list that contains each of these bands. We'll do, I think, RGB order. So band 4 first. Oh, I guess this needs to have a name. So I guess before I get too deep into the weeds here, and like I'll be upfront and say that this is like, we're working on an episode to show how to work with like time series, which I think will clear up a lot of these questions. Like this is something that I would probably like spend a little bit of time on. There's a library called StackStack that allows you to like query like a list of assets. So a lot of the things that we've shown today are going to look similar. You're going to get a list of items. This is also using the Sentinel-2 COGS example. And you can pass in an argument that specifies like a list of assets that you want. And so StackStack then takes this stack items, which is an item collection, and returns to you like a data array that might have like 13 bands and like 17 time points. So I'll just like post this link in the chat. This is like, this would be like what I would first go to if I wanted to like put together multiple assets into the same data array. I have in the past like done like a more like manual solution where I'm using something like xarray.merge, but I think rather than like work all that out on screen here, where I think I might flounder a bit, because I do rely on a lot on the documentation and like looking at references just like everybody else. I think we can instead like leave that time for more questions. Are there any other questions? Okay, cool. Well, Diego just posted some code, so yeah, let's check it out. Okay, so yeah, let's just take a look since there aren't any questions out there. So I think, Diego, an issue that's coming up here is that this is actually merging without accounting for that each of these need to be placed in a separate band dimension. So right now, this X-array that has been created is not actually a multi-band array. So that would need to be addressed. Yeah, and there's probably, if you look at like the X-ray merge documentation, there's, I think, some guidance or tutorials on like how to handle the dimensions properly there. I would definitely say though that like StackStack would be my go-to for like creating a multi-band array. It handles a lot of like, sometimes your assets are going to be in different projections and you're going to have to like resample one asset to another projection. Sometimes like you know, they might be on slightly different grids or like overlap partially or things like that. So it's StackStack like kind of handles a lot of that for you. It also gives you control like over the resampling method you can use. So we don't have a lesson up quite yet. This is like a lesson that's like still in development, but this would be, I think, what I would point folks to. Cool. I think if there are no other questions out there, I'll just mention, like, to give you a preview of like what is next in the episode. This next lesson is then going to switch gears and cover working with vector data in Python. And so it'll show you how to do a lot of the same things that we just did in like the raster episode, how to open a vector, how to look at the CRS attribute, the bounds, etc. This lesson focuses on GeoPandas as the primary package for inspecting and working with vector data, and allows you to plot vector data sets. So it has a very similar structure to the raster episodes. So yeah, feel free to check this out. Yeah, I'm happy to stick around for more questions. I think given the time we have, it's not quite enough to run through the vector data in Python, but happy to stick around in case folks have questions.
Well, thanks so much, Ryan. I think what we'll do is give you a big thank you and round of applause for today, and then we'll shut off the recording so folks can just chat a bit. But this was super exciting. I'm always pleased when I get something to plot and it's like, yay, image. So I appreciate that. And I learned a lot today. I think our learners here that are with me probably learned a lot as well. A big shout out, thank you to all of our folks who are helping in the chat, both folks we had planned on being helpers and folks who just jumped in to answer questions as we went, who had information. It's always a nice community here. And so I wanted to thank everyone, but especially Ryan today for presenting.